Alright, hello, here we are again for another lovely session of CENG 4412 Steel and Concrete Design. This video is going to be picking up right where the previous one left off. This is going to be the third video or the third part of the 15th lecture in the video series. And in the second part of this lecture, we looked at sort of the theory, from sort of base principles theory behind development length. And now we're going to look at how the ACI code handles development length in terms of code equations. So development length, or in other words, development length for design. Designing for development length. Designing for development length. Development length. And we're going to spend most of our time talking about tension reinforcement development length, but you also have development length for compression reinforcement, which is what you sometimes have for members where the concrete itself doesn't give enough compressive strength, need to add a little extra, and so you had compression reinforcement. Designing for development length. Well, first of all, let me just go ahead and state that we don't need to worry about any kind of phi factors here. So I can just mention that here. We don't need to have any kind of safety factors or that sort of thing. That's already sort of baked into all the equations that we're looking at. So no phi factors or factors of safety, etc. for this. And the first thing I want to do is talk about tension reinforcement. So tension reinforcement. So the first major topic is going to be tension reinforcement. And that's what we're going to spend most of our time in this video talking about. So let's look at tension reinforcement. Now, let's see. So I want to go over first a general equation, which is a gigantic equation. It's really big and really scary. And basically, let me give an outline for what we're going to talk about today. Or in this video. First, I want to talk about the tension reinforcement. And then under this, I'll have a sort of a general equation, a long general equation. And then we'll be looking at some specific simplified forms of this, simplified equations that are a little bit less scary than the big, scary, long general equation, and something that we'll tend to use more often. Then we can also talk about compression reinforcement. Compression reinforcement, and then we'll finish up 3 with just a discussion of some other things like hooked bars and other MISC details. And just a discussion of how, in general, of details, reinforcement details, hooked bars, and other details. We're going to spend most of our time talking about tension reinforcement here because this is still a reinforced concrete beam unit. So let's move on here. And other details. And when I say details, I mean steel reinforcement details. So first of all, let's look at the big, scary tension reinforcement general equation. This is sort of the granddaddy of all these. And this is let's look at the general. So maybe this would be 1A in my outline from before. This would be the tension reinforcement general equation. And this is going to be giant and scary and terrifying, but that's okay. It's Halloween. General equation. And the full form general equation is, now I mentioned this is a simplification from the theory that we've looked at previously, and at first you might think I'm lying to you, being simpler, but it is actually simpler than trying to take into account all the intricacies of cracked concrete. But anyway, LD here, LD is development length, but I'll see that. Let me just write the whole equation, then I'll define what all these things are. 3/40 times Fy over lambda times root f prime c times square root of f prime c, lambda times root f prime c, times a big fraction that consists of psi, 3 factors that are called psi, using the 3 factors using the Greek letter psi t, psi E and psi S. And this is then divided by the factor, or the quotient, CB. Now this is not the same CB as from steel. This is a different CB. It's not a moment distribution factor. It's something else. It's lowercase CB. CB plus capital T sub TR, KTR. So that's the capital letter K subscript TR, divided by dB, the diameter of the bar, and then close bracket and multiplied by the diameter of the bar. And the equation number on this, I'm going to try to do a good job here of citing all my equations. This is equation 25, again in the ACI manual, 25.4.2.3.A. Okay, so what is all this nonsense? Well, most of these things are going to help deal with things that, again, this is the general equation. And what I mean by that is this equation can be used for really any kind of tension reinforcement. It has a bunch of different factors to take into account everything that you might be experiencing. And so because of that, it's sort of a Swiss Army knife of equations. And because of that, it's fairly complex. LD is what we're actually after. This is the development length. This is the depth that we need to make sure that our rebar is embedded from one piece of concrete member to the next in order to transfer stresses. So this is very important when we get to connections. So for example, when you join a beam to a column, when you do that with steel, well, you can just weld steel together. That's very easy. You can add a flange plate, a web plate, whatever, weld it, bolt it, whatever you want to do. Concrete, you can't do that. So you can't weld concrete. Now, if you tried to pour wet concrete between two pieces of concrete, you're not going to get a weld. You're going to get a cold joint, a joint with no strength. And so instead, we need to use development length, where we actually have a piece of steel extending directly from one concrete element into another, and the length of that needed is going to be your development length. So LD is your development length. Fy is the steel yield stress. The steel yield stress. Lambda is something we've talked about previously. This is the lightweight concrete factor. Lightweight concrete factor. A lightweight concrete factor. So usually it's going to be 1.0 for normal weight concrete, but if you have other and so a lot of these factors like the size here and the lambdas, in most cases they're probably going to be 1.0, but if you have different things, they may not be. And then you also have, so let me define these psi's. Psi T, this is the casting factor, something called the casting factor, dealing with casting conditions. Casting factor. I'm not going to talk about all of these in great detail. I'm just going to mention where they're found. And they're just all described in a table, and you can read through the exact basically conditions that you have, and you'll select an appropriate factor based on that. Then you'll have psi E, which is the epoxy factor. This is used where you have some sort of epoxy coated rebar. So if there's no epoxy present, so epoxy is again something we add to. I don't know if I mentioned that in this class yet, but epoxies oftentimes will add epoxy to your rebar as a way of making it more corrosion resistant. But of course, that's going to dramatically change the skin friction, so in turn that will affect the development length. Psi S is the size factor, and psi S is the size factor. And then D sub B, dB, is just the diameter of the bar. Is the bar diameter. Now, most of these factors here, and I haven't gone through all of this, but let me just mention that here, all of these here, the lambda and the three psi's, these are all found in the same table in the ACI manual. This is found in to find these, it really isn't that hard. You just figure out what a case applies to what you're looking at, or to your particular system, or your particular structure, and you'll use table 25.4.2 0.4 to get the appropriate factors. Now, here, next on the next slide, I want to talk. So I've described everything here. Everything here is fairly straightforward, except I want to describe this quotient here, the CB plus KTR over DB. I need to describe this on the next slide. We refer to this as the confinement quotient, or the confinement term. This CB plus KTR divided by DB, this is the confinement term. The confinement term. And when you're working through these equations, no matter what your actual results are, this must be this must always be less than 2.5. Must always be less than 2.5. Now, that does not mean if you get something less, more than 2.5, you redesign. Rather, it's that you calculate this to the best of your knowledge, and then if you get, say, 2.6, well, then you use 2.5 instead of 2.6. So it's sort of like an upper limit. And the reason for this is that if you look at this, this term here, the larger this is, the smaller this is, and the smaller your overall development length. So it's actually you have a better interest in a larger version of this, because that would make your development length smaller. But they say, okay, well, regardless of what you actually have, we're not allowing you to go over 2.5 on that. But what does this mean? So in dB, that's just the diameter of the bar. That's not too bad. CB is something that you have to. That's also described in the same section of the manual of the code, and CB is going to be equal to the minimum of three things. You calculate three independent things, or you look at three independent things on your beam or on your section, and you pick the minimum one. This is basically a geometry factor. It's the minimum of the side cover in inches, the top cover to center of bars in inches, top cover to center of bars also in inches, also in inches, and 1/2 the bar center to center distance, C to C distance. So let me kind of draw these out and list some possible CB values, or list some possible measurements of CB. So basically, if you have a concrete beam here, and let's say it was something like this here, 2 pieces of rebar, 2 deformed bars, whatnot. So top cover to center of bar, well, that would mean like some sort of CB like this. That would be the, well, let me go in order. The first side cover would be something like this here, the side cover. Although if we look here at page, again, at 25.4.3.2, where it discusses this, it does discuss it. So I'm just getting all this directly from the ACI code, if you're wondering where this is coming from. I didn't remember this off the top of my head or anything. 25.4.2.4, sorry. Here, let's see, 25.4.2.4, yes. And where did that CB go? Yeah, here. Let me find that reference where I found this in the code. Yes, CB is the factor that represents the least of the side cover, the concrete coverage of the bar, in both cases measured to the center of the bar or the wire. So, in other words, this would be a CB value here, a possible CB value. This is what we mean by side cover, from the side of the beam to the center of the bar, or a top cover from the center of the bar to the bottom or the top of the beam, CB, or 1/2 the center to center distance, so something like this, CB here. So you're basically finding each of these measurements and going with the minimum one of these. So these are potential CB values. You look at, for your given piece of rebar, you look at what are each of these potential CB values and pick the minimum. And then KTR is another factor that goes into the quotient here, goes into the confinement factor term. And KTR is something we refer to as the transverse reinforcement factor. In other words, it is a factor that represents the confinement provided by shear reinforcement. This is the transverse reinforcement factor. The transverse reinforcement factor. And the formula for this is that KTR is equal to 40 times ATR divided by S times N. Not SN, not tin, but S times N, a quantity S and a quantity times N, called N. And this is equation 25.4.2.3.B. And what does this mean? Well, ATR is the total total area of shear reinforcement crossing the slip plane. Or in other words, the plane of the wherever your development length is, the plane of that, the total area within the development length of shear reinforcement crossing the plane of the development length of shear reinforcement crossing the plane, the slip plane of the development length, the slip plane of your development length, of the development length in question, and then also S is going to be the center to center spacing of shear reinforcement. The center to center spacing of shear reinforcement of shear or transverse reinforcement of your stirrups, basically. And N is the number of bars developed along the splice plane. Number of bars, the number of longitudinal bars. Of longitudinal bars being developed along the splice plane, along that particular plane. Anyway. So this is a fairly complex factor, a fairly complex factor in case you can't figure that out, in case you can't see that. Being developed, and you can read more about that in the commentary of the ACI manual. Developed along splice plane. Now, mercifully though, if you find all of this too overwhelming, one thing the code does allow you to do is this, because you're just adding this to here, CB is thankfully not too difficult to determine, DB is not too difficult to do, but this is fairly complex. You really need to know a lot about the geometry and any shear reinforcement present. But because shear reinforcement only helps you out, if you want, you can just ignore it. And so you can just say, well, conservatively, what if we just ignore the effects of shear reinforcement altogether and say, what we can just say KTR can conservatively be taken as 0. Can conservatively be taken as 0. As 0. Okay, so again, that is the general, and that really concludes the general equation. So this is the big, bad, scary equation. It's the long form equation, and it does work in all cases, but often it's going to be really too much for what we really want to use. It's a pain in the butt. It has all these different factors. We need to know a ton about the geometry of the setup. If there's some way we can avoid using it, often we will. So this is the general form. But then next I want to look at something I would actually tend to use more in design, at least if I don't have any kind of, unusual setup like epoxy rebar, that sort of thing. If I look at, I guess I'll call this section, what did I call that? 1B, I believe. Yes, 1B. Let me show the simplified forms. 1B 1B, and let me, what did I use there? Yeah, 1B, tension reinforcement, particular cases, or simplified equations. Reinforcement, simplified equations. Simplified equations. And this is going to be a table, and these can be found in table 25.4.2.2. Table 25.4.2.2. And what do I mean by simplified? Well, if you, I would encourage you, if you have your code in front of you, please go to this table. Let me actually go here, 25.4.2.2. And in my edition of the ACI code, the 31814, this is on page 415. And it just gives us a much reduced or a much simpler version of the kind of the equation here. It still looks more or less the same, but it's definitely simplified a bit. All of that shear reinforcement, confinement, all that kind of stuff disappears. And basically we have a table that looks like this. And the way I'm going to kind of classify this is basically small bars, large bars. I'm going to sort of approximate or simplify even further. So I'm going to sort of translate all the things there to a sort of simple case here. Small bars, large bars. And then for this case, this would be, I could call this maybe a short length case, short LB case, or LD case. We're allowed to use a shorter development length, and a longer development length case, long development length case. And then you just have a series of things. So small bars, it's fairly easy to tell whether you, this is fairly easy to tell whether you're using small bar, whether you fall into the small bar or the large bar column. Basically, this is just number 6 and less. So basically, this is small bars here would be bars that are number 6 and smaller. And here would be number 7 and larger. And larger. Number 7 and larger. And then there's going to be just a simplified factor for each of these, or a simplified equation for each of these. And for the small bar short LD case, and I'll talk about how we determine whether we're in the short LD or the long LD case. I'll do that on the next slide. But here, the formula is going to be, say, maybe 1 over 25 times a factor Fy, psi t, psi e, and these are the exact same things we already talked about previously, psi e, divided by lambda at root f prime c, times the diameter of the bar. And this is going to be the same for all 4 boxes. So for this one, you just have, all that's going to change is the number here, the coefficient. So we'll just have 120 times the same. I just don't want to have to write all that out. I don't want to have to repeat that. So same thing here. Let me just put a big bracket around that. Same thing times that same bracket. This is 350, 3/50ths times this times that same bracket. And this here would be 3/40ths times that same bracket. Times that same bracket. And then, so figuring out whether you're in the small, which column you're in is trivial, it just depends on the bar size. But then the short LD or the long LD case, now you can read through the verbiage there, but what I'm trying to do here is I'm trying to take this complex verbiage and just sort of simplify it down a bit. So how do you figure out if you are in the short or the long case? So I'm running out of slides here. Let me give myself some more slides. Man, that's how I know we're going too late into the night, when we're running out of slides. So here, how do we know that whether we're in the short or the long LD case? Anyway, so the short LD case is going to be better. You need less development length. And so basically by default, we're in the long case unless we can meet a particular set of criteria, two potential sets of criteria. So how do you know whether you're in the short LD development length or long LD case? Well, by default, you're going to be in the long LD case. By default, in the long LD case, unless you meet certain criteria. You use the long LD case unless you can meet one of two possible sets of criteria. You meet one of two sets of criteria. The first set, and within each set, you must satisfy all three of them, or all of them. So for set 1, the clear spacing, A, clear spacing is greater than or equal to the bar diameter. Greater than or equal to the bar diameter. B, the clear cover is greater than the bar diameter. Is greater than the bar diameter. And C, the shear stirrups are greater than the minimum required by code. Are greater than the min required by code. Are greater than the minimum required by code. And so, in other words, if you meet all three of these, you can use the short case. If you meet all three of these, meet A through C, A, B, and C, not or, but all A, B, and C can use the what I called the short case. And that's not something you'll see labeled in the code, but I think of it as the short development length case. You can use the short equations or the short development length. And then there's another set of conditions that will also allow you to do this. Set 2 here. This is where, or alternately, you can either satisfy this one or this one. A, clear spacing is greater than or equal to twice the bar diameter. Is greater than or equal to 2 times the bar diameter. And B, clear cover is greater than or equal to just the bar diameter. If you do that, if you have this, in other words, twice the clear spacing, then you don't need to worry about shear stirrups. But in turn, you're going to need twice the clear spacing. So if you meet both of these, then you can also use the short development length equations or forms. If you meet A and B can use the short development length equations. Or you could just be conservative and always use the longer form. When I say longer form, I don't mean the longer equation, but I mean the equation that will give you the longer development length. So you can use the longer form equation, development length equation. Or sorry, if you meet A and B, you're allowed to use the short development length equation. Basically, row 1. The short development length equation. I should actually say equations because there's the small and the large bars. Development length equations. Now, I know at first this does seem overwhelming. This is a lot of stuff, and it does seem kind of overwhelming at first. But the nice thing is that while this does seem overwhelming, really this doesn't necessarily, this often collapses into something much simpler. So I'm going to give an example that's actually included right here in the commentary. While this may seem overwhelming, often you can construct relatively simple expressions for say, development length. You can construct simplified expressions for development length. For development length, for example, here, often, for example, let's say you had here, for example, bottom bars. The example they give is bottom bars with sufficient cover, with normal weight concrete, which is going to be most of our standard tension reinforcement, with normal weight concrete, and then uncoated, so no epoxy, uncoated. So basically normal weight concrete, this means that lambda is equal to 1. Uncoated means psi e is equal to 1.0. And let's say it, and we have bottom bars. So here, bottom bars, so psi t, the casting, psi t is equal to 1.0. And let's say you have grade 60 reinforcement. Grade 60 reinforcement with F prime C equal to 4,000. Well, the LD would be equal to 60,000 times 1.0 divided by 20 times 1.0 times 1.0, assuming that you have sufficient clear spacing, etc. 1.0 times root 40,000, or sorry, root 4,000 times dB, and that would just equal approximately 47 dB. So many times a lot of these factors turned out to be 1, or it could just be 60,000, or you might be able to just reduce this to or alternately you might be able to do something like a simplified form of this, which would just be like Fy divided by root F prime C, maybe over 20 root F prime C times dB. A much simplified expression for development length. And this would be for any yield strength, for any F prime C, and as long as it was normal weight concrete, as long as it had sufficient clear cover, as long as many of the things that are almost always there are there, you can often collapse these into much more simplified expressions like this. So in other words, if you were doing a whole bunch of beams that had regular cover requirements, that had just normal concrete, normal steel, no epoxy, anything like that, you could just collapse this to a much more simplified equation. And that's even before we start worrying about any of the general equation, which is even more complex, of course. But that's the basic idea of development length for tension reinforcement. Next, I'd like to talk briefly about bars and compression. 3, I'd like to talk about bars and compression. Actually, sorry, I guess this is 2 I said earlier. 2, steel bars in compression, or rebar in compression. Rebar in compression, or I should say development length for compression reinforcement. For rebar for compression reinforcement, or rebar that's going to be in compression. Oh, and I should probably mention, I don't know if it was clear, but even on these simplified equations, we still have LD must be greater than 12 inches for compression reinforcement, for tension reinforcements. That's not going away, even though the equations are simplified over the long generic form or general form of the equation. And this one, thankfully, I'm not going to have to spend too much time explaining this, but this is found in, the equations for this are found in section 25.4.9.1, 24.4.9.1, and they introduced the quantity called L sub dc. LDC, which would be the development length for compression reinforcing. And again, like I mentioned previously, sometimes you'll have compression reinforcing when the concrete alone is not able to carry all the compressive loads. And yes, of course, you could just use a deeper beam or something, but then your weight increases. So maybe you're very limited in the size of beam you can use, the physical geometry, the physical dimensions. So you'll add compression reinforcement to beef up the strength of the beam. But LDC is actually going to be the max of. Well, we have the same we have the same sort of minimum length, and that's going to be 8 inches. So well, there's a couple different things here, but I've just kind of baked them into one expression here. The max of 8 inches, and then a factor, a quantity or a calculation called, or an expression, Fy times psi r, different psi this time, divided by 50 times lambda, times lambda times square root of f prime c, all of this times the diameter of the bar, dB. And then we also have 0.0003 Fy psi r times dB. And these are found and discussed in section 25.4.9.2, those two, where those calculations come from. You can read through that section. And the two factors here, well, lambda is the same as we've always seen. That's the lightweight concrete factor. The lightweight concrete factor. And psi r is the confining reinforcement factor. So similar idea as what we had in the tension reinforcement, except you can just look up the value in the table. It's a little bit simpler. But you can read up on it there. I don't know if I want to go through all of this in class. Concrete reinforcing factor. Yeah, in class, not video recorded at 11 o'clock at night before class. The confining reinforcing factor, or I should say reinforcement factor. And this is found in table, to find out what these are, to find the values of these, this can be found in table 25.4.9.3. If I have my citation correct, 25.4.9.3. And then finally, section 4 on my outline here for development length of code. I just want to say that I just want to give you some appreciation that there are many, actually I guess this would be section 3 in my outline, that there are many other details possible. In this course, we are only going to just scratch the surface of the detail requirements for the concrete. The term, when I say detailing, I mean the same term applies to many kinds of engineering. When we say detailing, we're talking about the minor details, the small connection details, the small, not the grand scheme of, if I'm talking steel detailing, I'm not talking about, select a W36 by whatever. I'm talking about, okay, well, here's the welds that you use. Here's the kind of bearing plates that you use. Here is the exact size and pre-tensioning of the bolts and all this kind of thing. That's detailing. And so there are many other kinds of detailing and cases that exist. Kinds and cases of detailing that exist and need to be considered by a design engineer. Of detailing that must be considered by a design engineer. Be considered by a design engineer. By a design engineer. A design engineer. Engineer. And one quick example. We can't possibly go through all of them in the time for our course, but an example would be something like hooked bars. if you find that you do not have enough development, enough physical length in your beam or your member to produce the full development length, often you can do what is known as using a hooked bar. And this is a bar that is literally shaped into a hook. So if you think about it, the normal steel that we've been talking about, we've been saying, okay, well, we have a piece of steel and it's embedded within concrete, and it's basically transferring that load via skin friction. Well, what if instead, if we find that we can't get enough length here, what if we made the bar into a hook? And so when that bar wants to pull out of the concrete, the only way it can do that is by tearing through a massive amount of concrete. So it's a lot. It's going to be. Imagine if you took your rebar and curved the end of it literally into a hook like this, like a 90-degree bend. And now, if you want to pull this thing out, you're going to have to pull out a massive chunk of concrete. So this is what we refer to as a 90-degree hook. A 90-degree hook. And you could also have a 180-degree hook. And there's a whole bunch of details that go into how to size these, things like the minimum radius, that kind of thing. All of these this would be like a 180-degree hook. And these can be discussed in table, and these are discussed in the table and the discussion at the section around table 25.4.3.2. And that's just one example of the other details present here. But really, all of chapter 25 covers details for reinforcing. All of chapter 25 covers details. Chapter 25 covers these kinds of reinforcing details. And so you literally need an entire large chapter in the manual or in the code to describe this. So as you can tell, this is quite involved. Covers details that exist in various applications. In various cases. So things like, okay, well, how do you handle where a column meets up with a beam? How do you tie those together? How do you handle things like seismic detailing? How do you handle things like the detailing for pretension wires and deformed wires and all these types of things? And you can read through all of this, and it has a lot of standard details and that kind of thing. How do you handle a beam coming into a girder? How do you handle bearing surfaces? Just all sorts of things, and there are all sorts of very particular requirements, and that many of them probably go a bit beyond the scope of this course. And sometimes when you take a more advanced, say graduate level advanced concrete design class, sometimes you do discuss those there. And I would go into this in greater depth if we were teaching maybe a pure concrete design class or a graduate level or advanced concrete design class. But I think in terms of concrete detailing, I think that will do it for our discussion of development length here. All right, that'll do it for this point of the portion of the lecture, and thanks for watching, and as always, thank you.